Hello again, this is Math 2115, remote delivery for April 21, 2020, and this is part one of two parts. This deals with spanning trees and minimum spanning trees in a graph, and I encourage you to use this button to pace the delivery as well as to practice some of the problems that I pose. And at the outset, I try to say something encouraging, and this is a quote that I ran across earlier today. And the quote says, "Carpe Diem," that is Latin, and that's Latin for seize the day. Make your lives extraordinary. You see, you really are doing something extraordinary. In very unprecedented times, you're engaging in your coursework, you're earning grades, and grades will be rendered. Your goals, educational goals anyway, need not be deferred. It is something extraordinary that you are doing. One of my favorite films is called Dead Poets Society. Many of you perhaps have not seen it, and if you type this kind of thing into a search bar, you'll see it. This movie stars, among others, the late, great Robin Williams, and this lecture is kind of sobering, but very true. As an introduction to today's topic, suppose that an airline company wants to expand the service to the Midwestern part of the United States and has received permission from the regulatory body, the United States Federal Aviation Authority, to fly any of the routes shown in this figure. And the company wishes to legitimately advertise service to all these cities shown, but for reasons of economy wants to use the least possible number of individual routes to connect them. Now, one possible route is given in this figure. Now, clearly, this network, this system, joins all the cities. But the question could be, is the number of individual routes minimum or not, minimal or not? And the answer is yes, and the reason might surprise you. You see, the fact is that the graph of any system of routes that satisfies the company wishes has to be a tree. Because if the graph were to contain a circuit, then one of the routes in the circuit could be removed without disconnecting the graph. That's a lemma we talked about earlier. And that would give a smaller total number of routes. Now, any tree with 8 vertices must have 7 edges, and therefore if we count the number of edges up here, we end up with 7. So therefore any system of route that interconnects all 8 vertices and minimizes the total number is 7 vertices. So this in fact does solve that problem. Also motivates a definition and a theorem. And in fact, in general, problems like this are called finding a spanning tree. So the definition is a spanning tree for a graph G is a subgraph of G that contains every vertex of G and is a tree. And you can think about many applications of this. These could be postulated as a theorem. Every connected graph has a spanning tree, and any 2 spanning trees for a graph have the same number of edges. Let's look at a formal proof of this. Suppose you have a connected graph. G is a connected graph. If G is circuit-free, then G is its own spanning tree, and we are done. If not, then G has at least one circuit. We could call it C1. And by the lemma that we studied earlier, the subgraph of G obtained by removing an edge from C1 is still connected. If this subgraph is circuit-free, then it is a spanning tree and we are done. If not, then it is at least one more circuit, C2, and as before, we can remove an edge from C2 to obtain a connected subgraph. Continuing in this way, we can remove successive edges from circuits, and eventually we obtain a connected, circuit-free subgraph T of G. This must happen at some point because the number of edges of G is finite, and at no stage does removal of an edge disconnect the subgraph. Also, T contains every vertex of G because no vertices were removed in constructing it. Thus it is a spanning tree. The proof of the second one follows readily and is shown here in red. I typed it in. Any two spanning trees for a graph connect all the vertices and say there are n vertices. Then a tree in a graph with n vertices has n minus 1 edges. Therefore, any spanning tree for a graph that has the same, for this graph with n vertices has n minus 1 edges. Alright, so here's a problem for you. I'm asking you to find all spanning trees for the graph pictured below. Hit pause, solve the problem, and then return. Let's see how you did. Let's see how you did. You see, this graph has one circuit, and it's V2, V1, V4, and V2, and so you can remove any edge of that circuit, and there are three of them, and so if you remove that, you get the following three spanning trees for G. Now, further, suppose that the airline company wants to serve all of the cities as shown, but now they want a route that minimizes the total mileage of the system as a whole. Note that such a system is a tree, because if the system contained a circuit, you could remove an edge from the circuit and it wouldn't affect a person's ability to reach every city from every other, and again by the same lemma, but it would reduce the total mileage of the system. This motivates the following problem and the following definition. A weighted graph is a graph for which each edge has an associated positive real number weight, and the sum of the weights of all edges is the total weight of the graph. A minimum spanning tree for a connected weighted graph is a spanning tree that has the least possible total weight compared to all other spanning trees for the graph. And some notation that often gets used: if G is a weighted graph and E is an edge, then W of E denotes the weight of E, and W of G denotes the total weight of the graph. So, the problem of finding a minimum spanning tree for a graph certainly can be solved. One solution would be to list all spanning trees for the graph. Remember that we found all the possible spanning trees. Compute the total weight of each and pick the one which is a minimum. And some fancy math that we talked about earlier in the course does guarantee the existence of such a minimum. Actually, this was one of the sections that we skipped, but it is an important theoretical principle, although it is considered optional for our course. Serious students may want to go back and read about this in an earlier chapter. This solution of listing all the things is a brute force solution and is inefficient in its use of computing time because the number of distinct spanning trees can get very large. For instance, if you have a complete graph, now a complete graph is one that is completely interconnected, so every vertex is connected with every other one. And if you have n vertices, there are, and a serious student might want to try to prove this, but there are n raised to the n minus 2 possible spanning trees. Now, if this number is a big number, for example, 100 vertices, it would be 100 raised to the 98th, which is an enormous number. Even using the fastest computers available today, if you had to examine all trees in a graph, that would require more time than is estimated to remain in the life of the entire universe. Not only our lives, but the lives of the entire universe. Now, this problem has been studied by very smart people. In 1956 and 1957, Kruskal and Prim separately each described much more efficient algorithms to construct minimum spanning trees. Even for large graphs, both algorithms can be implemented so as to take relatively short computing times. And you might say, this sounds a little bit familiar, and it is closely related to a problem we studied before. In 1959, and notice that the progress was rapid. 1956, 1957, and 1959, the computing pioneer Dijkstra developed an algorithm, and we studied this earlier, to find the shortest path between a starting vertex and an ending vertex in a weighted graph. in which all the weights are positive. Now you see this is solving even a different problem. It's solving a larger problem. But it is similar to what Prim's algorithm in that it works outward from a starting vertex A, adding vertices and edges one by one to construct a tree. It differs from Prim's algorithm in the way it chooses the next vertex to add, ensuring that for each added vertex V, the length of the shortest path from A, the initial node, to V has been identified. In part 2 of today's lecture, we consider these algorithms and solve some associated problems. See you in